Hi, hello, and welcome. I'm Greg Jacobs. I teach at Woodbury Forest School, a boys' boarding school in Central Virginia. In the before times, I'd be sitting right over here at my desk with music playing, while 15 or so students worked in the lab behind the camera that I can see. They'd be talking to each other about practice problems. They'd be showing their work. They'd be doing experiments and coming up to the front of the room to show me what they've done. April is the best time of year in AP Physics 1. It's the time to put it all together, to figure out not just how to use the disparate skills you've been taught, but when those skills should be applied in the first place. And the time to do all that putting together is now. Learning physics is like preparing for the conference swim championships. See, my wife Sherry was a college swimmer. She spent December and January in grueling multi-hour practices, building muscle and technique. She was so tired from some of these that she often didn't have the energy to walk across campus to get dinner. She'd instead eat 5 or so of the excess grapefruits that I was sending her from my backyard tree. But then in the weeks before the championship, the team tapered. They still practiced every day, but they practiced less and less intensely. The goal was to maintain, not to build. And so it is in physics. You've spent the year building your knowledge. Now it's time to start tapering. Do a released AP problem. Use an authentic one from AP Classroom that your teacher assigns. Use one from my book. Use one from a good source. Then don't ask for help. Don't ask for clarification questions. Just do the problem as if it were an exam. Then show your work to a teacher or a friend, or even to me. Right or wrong, you'll have learned something. It's totally fine to make a mistake. In fact, now is the time to make mistakes so that you don't make them on the actual exam. Redo the problem, though, until it's right. Then move on to another one. The goal is to do a little bit every day to maintain your physics skills. See, if you're watching this, you probably are taking more than just one AP exam. You will be so busy in May that you won't have time for serious in-depth physics study. So don't plan on doing that. Plan on doing the serious in-depth study now. Plan on doing one multiple choice practice question a night in May. And then the night before the exam, plan on having a not physics party. When I taught in Florida, my night before the exam party was on the beach. Here, it's been at the pool or at the snack bar. You see, there's nothing more you can do the night before the exam, any more than a football team can build their strength through a 4-hour weightlifting session the night before the Rose Bowl. So work now. Make your mistakes now. Correct your mistakes now, and you'll build your confidence for May 14th. Now, on to the problems from the other day. Last Friday, we covered forces and equilibrium, and I posed 2 sample questions here, and I have not just the answer, but a demonstration for both. The box pictured moves at a constant speed to the left, and we want to know which of those is the correct relationship between the tensions. If you recall, we said that anytime you have an equilibrium question, we follow our 2-step procedure. Step 1, free body. Step 2, if necessary, break angled forces into components. And step 3 was to write the equilibrium conditions. Left equals right, up equals down. So let me do that. I don't care what the problem asks for. It's an equilibrium problem. I've identified that. So I'm going to do my 2-step procedure. I've got, I forget which one is which. I think we got T1 here. We've got T2 here and T3 here. We also have vertically, we have a normal force, the force of the surface on the object, and we have the weight. But in the horizontal direction, which is what the question asks about, we can say left equals right. Well, that's T3 equals T1 plus T2. All right, now we go back to the screen share and see what the question was actually asking for. Oh, there's our answer, choice D. That's all there is to it. Now, wait a second, you all are saying. Wait a second. The box was moving. Doesn't the force in the direction of motion have to be bigger? How did it get moving to begin with? All right, I understand you have that question, but the answer is still that the tension to the left equals the tensions to the right. The question of how did the object get moving is irrelevant. I mean, how did the universe start? That doesn't matter. All that matters is what's happening right now. Whether the block had to have a bigger force to the in the direction of motion to speed it up, well, that might be true, but that happened before we started the problem. Don't mess with my story. The story starts with a block moving at constant speed. And you say, but wait, if something is moving to the right, there have to be more forces to the right. Can you see this? I've got equal forces on each side of this platform. And so this little thing in the middle is in equilibrium. But imagine now that I did this experiment in a van moving at constant speed on the freeway, 60 miles an hour in a straight line. Oh, are you telling me that, oh, since we're moving 60 miles an hour that way, I have to put way more force on this way? It's going to fall apart? No, you still need the same force on each side to balance. Equilibrium applies even when an object is in motion, as long as that motion is constant speed in a straight line. Second problem. Share screen. Second problem, we have a block that's sitting on a rough surface and I'm pulling the block at an angle. We want to know about the normal force on the block. Let me do the free body diagram again. Once again, it doesn't matter what the problem asks for. I didn't read what the problem asked for because I recognized an equilibrium problem, and now I'm going to do the equilibrium problem. The free body diagram includes a tension up and to the left, or up and to the right, a friction force, the force of the surface on the object backwards, a normal force, the block is on a surface, which means there is a force of the surface on the block straight up perpendicular to the surface, and the weight down. Step 1A asks us to break angled forces into components. Well, the tension is an angled force. So I have T cosine of whatever angle that was, and T sine of whatever angle that was. I still have the normal force, and I still have the friction force and the weight. This object is in equilibrium. Therefore, the friction force is equal to the horizontal component of the tension. But vertically, up equals down. So here is my statement of equilibrium in the vertical direction. So the question asked, explain why the normal force is less than the weight of the object. Well, because if I solve for the normal force algebraically, that's going to give me the weight minus the vertical component of the tension. This is going to come over here. So the normal force is going to be something less than the weight of the block. Do you believe that? Well, I've got the demonstration for you. Now, I know you probably can't see the numbers on this scale, but right now it reads about 3 newtons. And if I pull up into your left, oh, look at the numbers going down as I pull harder and harder, because the normal force, the reading in the platform scale, is going to be the weight minus the vertical component of this tension. And as I pull harder and harder, I get a smaller and smaller normal force. Isn't that cool? All right, let me outline today's show for you. We had our discussion of tapering. We've done our equilibrium of forces review, and now we are going on to the definition of acceleration, eventually a qualitative-quantitative translation problem. Edna is going to ride on this cart, and we're going to predict her speed. And I really want to call your attention to number 6. Stay with us toward the end, because in the last 10 minutes or so, I will be taking your questions at Jacobs Physics on Twitter. Go ahead and tweet to me. I will answer your questions as we can. Big shout out to all the physics teachers who are out there who are also answering the questions, including Mr. Williams of Cypress. Oh my goodness, of Cypress Ranch High School. All right. So, definition of acceleration. Here are 4 facts about acceleration. Screenshot this. These are the most important facts you can understand about acceleration. Notice there's no equations here. People think that kinematics is all about plugging numbers into those 3 basic kinematics equations and getting another number. Everyone out there who asked me, do they care about significant digits on the AP exam? You're asking the wrong question, because there will be vanishingly few numerical answers on any AP exam, let alone the one this year. It's not about plugging numbers into equations. Physics is about understanding the natural world and describing the natural world, sometimes with mathematics. So instead of trying to find what number do I plug in for A, let's understand what acceleration means physically. You probably have learned a mathematical definition of acceleration with a delta V over delta T. It's not wrong, but I'd rather you use what's on the screen. Acceleration tells us how much an object's speed changes every second. That's something to write as a starting point to so many problems. And then those second two tell us which direction acceleration is. Notice it doesn't say anything about positive or negative. It just says which direction acceleration is, depending on the direction of motion. So let's show you my toy here. Edna will have to go over here for a little while. Don't worry, you get to ride the cart in a bit. I've got a toy here. This toy is called a visual accelerometer. It's got an accelerometer built in here, the same way you have probably in your phone. And the only difference is the accelerometer reads out visually. Green arrows or green lights indicate acceleration to this direction, and red arrows indicate acceleration in that direction. So here's the first question I'm going to ask. I'm going to drop this cart and I'm going to let it go. And I want to know which color lights will be on, the green or the red. Don't answer yet. You don't want to say, oh, red, red. Oh, no, green, green. No. Start with the fact. The fact is, when an object speeds up, its acceleration is the same as its direction of motion. This object was speeding up. Therefore, while the object speeds up, the direction of motion is the same as the direction of acceleration, and the green lights will go on. You ready? Here we go. Green lights were on. But what about when I stopped the cart, like right now? When I was pushing the cart to stop it, which lights will be on then? Once again, start with the fact. Don't start with the answer. The fact says when an object slows down, acceleration is opposite the direction of motion. This cart was slowing down when I touched it because the cart was going pretty fast, and then I brought the cart to rest. You have to slow down if you're coming to rest. So this cart slowed down. Which way was the cart moving while it slowed down? Well, I didn't push that cart so it was moving back up the incline. All I did was bring the cart to rest. Therefore, the cart was moving that way, but slowing down. The acceleration is opposite the direction of motion when something slows down, so the red lights should go on. Do you believe me? Red lights went on, didn't they? One more time. This is fun. Green and then red. All right. Pause for a moment. Edna, hold that cart there. I want to pose another question to you. Consider this cart right now as it's speeding up. And consider a 747 wide-body airplane at cruising altitude going in the neighborhood of 600 miles an hour, in the neighborhood of 250 to 300 meters per second. Which has a greater acceleration amount? That is, which has a greater magnitude of acceleration? Acceleration isn't the same thing as speed. We answer by starting with the definition of acceleration. Say it with me. Acceleration is the change in an object's speed every second. This cart here was changing its speed every second. The 747 was not changing its speed at all. Therefore, the 747 has no acceleration. This has some acceleration, and some is bigger than none. Acceleration is the change in an object's speed every second without respect to how fast the object is moving. All right, back to this guy. Two more. This time, or three more actually. This time, I'm going to push the cart so it starts going up the hill, like this. And I want to know, while I'm pushing, right Now, until I let go, which lights will be on? The red lights or the green lights? When an object speeds up, which is what was happening while I was pushing, the cart's acceleration is the same as the direction of motion. The cart was speeding up and moving this way, therefore the acceleration was also that way, and the red lights will go on. There we go. Now, once I let go, the cart is slowing down. Which lights will be on? When an object slows down, the acceleration is opposite the direction of motion. The motion is that way, the acceleration is that way. The green lights show up after I let go. Boop. Red and then green. Final question. If you can get your hands on one of these, they are fun. Final question. I'm going to push this, and then I want to know right there at the top. Right there at the top. Which lights will be on? So, and I'll say, guys, don't troll me. When this cart reaches the top, the cart has to stop for a moment in order to turn around. And when something has no speed, it has no acceleration, and therefore there will be no lights. The green lights will be on, and then they will shut off very briefly while there's no speed and therefore no acceleration, and the cart will go down, right? Everybody understand? So let's watch these green lights. Okay, let's watch these green lights go on, blink off for a moment, and then come back down. Ready? Oh, wait a second. Green lights, go off. How can this thing not have the green lights off? I mean, there was no speed for an instant, so there can't be any acceleration, right? Well, the universe is telling me otherwise. The universe is telling me that when this cart has no speed, it darn tootin' has acceleration. And that acceleration is still down the ramp. How can we understand this? Well, let's go back to our definition. Acceleration is the change in an object's speed every second. Even when this cart was at the top of its flight and it reached zero speed, its acceleration was not zero. Why not? Because the cart was still changing speed. The cart slowed down to rest and then sped up. There was never a point when this thing was not changing its speed. There was never a point when the cart was at rest and staying at rest. The cart was always changing its speed. Two other ways to think of this. You can make a velocity time graph of this, and you will see. Here, I'll do it for you. There's the velocity time graph. And if you look right here at the 0 mark, that where the vertical axis value is 0, that's where the cart briefly came to rest. But the slope of a velocity time graph is acceleration, and the slope was never 0. And finally, you can think of a force argument. There was always a component of mg that was causing this acceleration. So a component of gravity was causing this acceleration. So what we're saying is, if the acceleration were truly 0 at the top, that means that somebody was manning the gravity switch and saying, oh, wait, there's somebody doing a physics demo. The cart's at the top of its flight. Boom, I got to turn off the gravity switch for a moment. I don't think that happened. So Occam's razor suggests that there is acceleration at the peak of the flight. However you understand that is fine with me, but you got to understand it. All right. Now is time for Edna to entertain you momentarily, because I'm going to take about 20 seconds and move this camera back for our qualitative-quantitative translation question. And while we're doing that, let me share the question with you. Here is the question. Read it, Edna, do a dance, and I'll be right back. All right. Thank you, ma'am. Derive an expression for the distance that the cart travels up the track before coming to rest. Wait, what's happening here? We've got a cart that's moving with an initial speed and an acceleration. So now you can see this. Oh, I'm going to have to take my Edna fan art down so you can see this. I love this, by the way. Thanks, Aldiscary. There we go. That's the first situation where the cart has an initial speed, v1, and an acceleration, a1. What are those values? I don't know. I don't care. They're given in the problem, and the question asks for a derivation. We're doing a derivation. That means communicate in mathematics, not in words, although you can annotate the calculation. But we still do the problem the same way we would do any kinematics problem. We choose one of the three kinematics equations that are on the equation sheet for AP Physics 1. We choose the one that includes initial speed, acceleration, and distance, because those are the three variables we're asking about. So that would be that's what you're going to see on the equation sheet. We know that our initial speed or our final speed is 0 because this thing comes to rest at the top of its flight. So now I can just solve and call that distance d. I'm going to solve for delta x. The negative sign's going to go away. Don't worry about negative signs. You can just forget about them most of the time. In this case, because the thing was slowing down, velocity and acceleration had to be in opposite senses. So one of them's positive, one of them's negative, and the mathematical negative sign here goes away. But we have to answer now in terms of the variables the problem gave us. The problem gave us not delta x, but it said d1. The problem gave us not initial velocity v0, but v1. And the problem told us the acceleration wasn't just a, it was a1. There's my answer. The derivation starts with an equation on the equation sheet. It plugs in the 0 here. I could even annotate this and say, hey, final speed was 0, and then solves mathematically, plugging in the variables that we're talking about. All right, there's our answer. Part 2. Oh my gosh, and I did all that where you couldn't see me because I had the screen share up. There, that's what I was doing. You couldn't see me, but it's up there now. Great, moving on. Back to the screen share. The question asked, in a new experiment, the cart's initial speed is tripled, and we want to know about the maximum distance the cart travels up the track. All right. Well, we know that the cart's speed triples. So when we triple the speed without changing the acceleration, we've got to triple the distance the cart travels. So here's the first situation where the cart goes from the 25 centimeter mark. I have a marked track here. I mean, I could put a meter stick up there if you wanted to, but I have the track marked every 5 or 10 centimeters. It's very clear on the track how far this has gone. This went from the 25 centimeter mark to the 40 centimeter mark. It went this far. That's 15 centimeters. So when I triple the speed, how do I triple the speed? Well, I click this not once. If I click it once, then I get the 15 centimeters that I showed you. I'm going to click it 1, 2, 3 times. Now, this cart is going to give me 3 times the initial speed. I don't know what that speed is. It's 3v1, all right? So that'll go 3 times as far. So it should probably go 15, 30, 35, or 50, 30, 45 centimeters. So that'll go from here to here, here, and here. It'll go right here. Ready? Oh no. I tripled the speed and I didn't triple the distance traveled. Why not? Let's look at this equation here, because the problem did say to show what features of your calculation apply to your reasoning. Well, let me try the factor of change method with this guy. If I do factor of change, if you recall, that means I plug in 1 for anything that doesn't change. I plug in the factor of change for anything that does change. The initial speed tripled. The number 2 does not change, so I plug in a 1. That's the key part of the factor of change method. Robin Mooney another physics teacher who works with me and was on a call with me the other day. She calls this the rule of ones. If something doesn't change, the rule is plug in a 1. And then the acceleration didn't change either. So what's the factor of change for this whole situation? 3 squared over 1, which is 9. That means this thing should go 9 times farther, not 3 times farther. Is that the case? It went 15 centimeters the first time. That means it should go 15 times 9 equals 135 centimeters the second time, which means, yep, that's 9 times as far as this. It went, it started at the 25 centimeter mark. So it should have gone to the 160 centimeter mark. It ended up at the 158 centimeter mark. Close enough. All right. So let me ask you one more question then. Screen share. Part 3. In a third experiment, both the cart's initial speed and the cart's acceleration are tripled. And we want to know how far up the track does the cart travel? Those of you who are answering quickly are saying, well, it certainly makes sense to me. I'm going to triple the speed, which makes it go farther, but I'm also going to triple the acceleration. Since this thing is slowing down, acceleration is opposite the direction of motion, and the bigger the acceleration, the more this slows down every second. That's the definition of acceleration. The more the speed changes every second, the more the speed drops every second. So a bigger acceleration means less distance traveled. And since we're tripling one and tripling the other, it should go the same distance, the same 15 centimeters that it just went. Let's check it out. So here's the original. This thing goes 15 centimeters from here to here. So when I both push this in to triple the speed and triple the acceleration, how do I know I've tripled the acceleration? Well, I marked this beforehand, but I've got my little app. You can't see it. I didn't show it to you at first, but I have this and it showed me the angle of 3 degrees to start with and now 9 degrees. By tripling the angle, for small angles this works, I've tripled the acceleration. So when I let this go, it should go the same 15 centimeters again because I've tripled both the speed and the acceleration, and it should end up right here and not again. Universe and I are going to have some words because you see, just because I want some 2 triples to cancel out doesn't mean they always do. Let's use the factor of change method again, please. In this case, I tripled the initial velocity, so I plug in a 3. The number 2 doesn't change. That's the Mooney rule of ones. And the acceleration tripled. So how does this work out? 3 squared divided by 3 times 1 is 9 over 3, which is 3. The distance traveled up the ramp should triple. And it did. Went, instead of 15 centimeters, it went 45 centimeters up the ramp from here to here. Isn't that nice? Physics works. The one more point I want to make about this particular experiment, this particular problem. Look at the wording in problem 2. Explain in words the features of the derivation in 1 that led to your answer in 2. That right there is the heart and soul of the qualitative quantitative translation. And remember, the May 14th exam will have 1 qualitative quantitative translation questions. You'll be asked to solve a problem in mathematics. You'll be asked to explain something conceptually about that problem, and then show what features of your calculation correspond to what features of your physical reasoning. In this case, if I were explaining this, I would explain that since the speed is squared and in the numerator, tripling the speed multiplies the whole term by 9. And since the denominator didn't change, the distance traveled multiplied by 9, not 3. That was the answer to number 2. For number 3, if I needed to do the qualitative quantitative translation, I do the same thing and just describe that, hey, although speed and acceleration are in the numerator and denominator respectively, since speed is squared, then that is going to multiply the term by 9, whereas the acceleration multiplying by 3 only divides the whole term by 3, and therefore I get 3 times the distance. All right. Cool stuff. One more problem for you before we do the question and answer. And while we're at it, at Jacobs Physics, please send in your questions, stories, and comments, and I will get to those in a couple of minutes. I got one more problem I want to do. I've got my cart, and I'm going to let it go from the from right here, from basically a meter above the bottom here. Little over. Let's go right here. So let it go. Boop. And I can measure the speed at the bottom. How can I measure the speed at the bottom? Because I can start recording. And the maximum speed is 1.4 meters per second. All right. So my question is, if instead releasing from the same spot, sure I did that right. Yeah, I did. Releasing from the same spot, I'm now going to have Edna ride. Remember, Edna has a mass of 600 grams. This cart is 250 grams. So I've more than doubled the mass of the cart. And the question is, how fast is the Edna cart system going to be going at the bottom? Well, obviously the heavier thing goes faster, right? But all right, so 2 or 3 times today, the obvious answer, the instinctive answer, the answer that we're all sure is right has been wrong. So maybe I better check. You never know, it could be right, but let's check. How would I find the speed at the bottom? I'd use one of my other kinematics equations. I would use, well, I guess I'll use the same one. VF squared equals V naught squared plus 2A delta X. In this case, we're starting her off from rest. And the acceleration is the same because we're on the same track. So let's just solve for the final speed. Let's do the factor of change. The number 2 does not change. The acceleration didn't change because we're on the same track. And the distance down the track doesn't change because I'm still going 1 meter. So how did the final speed change? That means, wait. What this equation is telling me is that when I release Edna with the cart, Edna and the cart will be moving the same speed as they were before when they reach the bottom of the track. Well, let's see which is right, your instincts or the mathematics underlying the physical world. Let's check it. And lo and behold, you got the same 1.4 meters per second. See, look at that. They went the same speed at the bottom. Turns out that your instincts about physics, and even, in all honesty, my own instincts about physics based on our experience, are often wrong compared to our understanding of physics through the mathematics that underlies these problems. That's the whole point of the qualitative quantitative translation and the factor of change method. All right, those are my demos for you today. It is time to go to @JacobsPhysics and let's answer some questions. Prabhav, I hope I pronounced your name right. I'm sorry, this is a visual medium. I can't do anything about it. Says, I don't understand how by changing the angle of incline that you change the acceleration of the cart. Please explain. Happy to. I skipped over that in a deeper way. You can trust me on it for one thing, but if you don't want to trust me, and good for you, know that this thing was sliding without friction, and as long as there's no sliding, as long as there's no friction, no rotation, then we can draw the free body diagram that looks like this. We've got this way, Fn, mg, and that's it. We can break up the weight into components. This is what we do whenever we're on an incline. That goes with mg cosine theta this way and mg sine theta along the incline. If you're ever confused as to which goes with which, sine slides. So mg sine theta is the net force on this cart in the direction of motion. So we set the net force equal to ma, cancel the masses, and the acceleration in this case is g sine theta. G doesn't change, but if I change the angle of the incline, I change the acceleration. Folks, this is not an equation to memorize. Notice that I went through my three-step problem solving process to get that. But this is showing us that in this case, by changing the angle of the incline, I change the acceleration. And then for small angles, plug it into your calculator. Not that we'd have to do this on the AP exam, but when I went from 3 degrees to 9 degrees, you'll see that I essentially tripled the acceleration. I have Ethan says, difficulty remembering the formulas. And should I be memorizing the formulas, or is there a better way how and when to know how to use different physics equations? Great question. You will have access to the formula sheet on the AP Physics exam, this and every year. On one hand, don't memorize the formulas. They're right there. On the other hand, if you know the formulas, then you know what you're looking for. Just make sure that you don't turn AP Physics 1 into a game of hunt and peck on the equation sheet. I'll tell you, Physics C people are way more guilty than Physics 1 people on this account. But I have read AP Physics exams since 1999, and I remember on the old Physics B exams where you had all kinds of different topics and equations. They had an equation sheet, so the students would say, oh, look, I'm looking for momentum. P equals mv. I know the mass. So what's P? So I have this pressure. This pressure in the container is 130 kilopascal. So I'm going to plug that in for P, and I'm going to just plug in my mass for M. And I wonder about the V. Oh, the V is for voltage. I'll go. Maybe it's 12 volts. I don't know. I'm not kidding. People did that. That's called hunting and pecking. If you don't know what you're looking for on the equation sheet, you're not going to find it. So have an idea of the kinematics equations, but then when you're actually doing a problem, just look it up to be sure. If you don't remember that VF squared equals V naught squared plus 2A delta X, if you're not sure, is that the 1/2 AT1? I don't know. Just look it up, and then you're sure to get it right. Great question. All right. Rebecca asks, how does the acceleration stay the same if I put Edna on the cart? If I put Edna on the cart, the mass increases, which means the weight increases, which means the component of gravity parallel to the cart's track increases, which doesn't mean the acceleration increases because it's the same problem here. Notice the masses cancel, Rebecca. Since the masses cancel, my acceleration does not have an m in it. And that's good qualitative, quantitative translation answers. Since when I solve out here, the mass cancels away, that means the acceleration doesn't depend on the mass. And since there's no mass in here mathematically, the mass shouldn't matter in the physical world, which it did not. That's a great question, Rebecca. John Norris asks, when asked to explain a derivation, should we only use words or can we use numbers in addition? For example, the expression becomes this and then explain what that means, or do I need to only use words? In general, when you're asked to explain something, and this applies to a paragraph response as well, you may use brief snippets of mathematics as long as they are part of a sentence. So I would say, I would do the factor of change out, and then I would write a sentence that says something like, I know that the distance down the plane will be multiplied not by 3, but by 9, because there is a v squared in the numerator of my equation. And that means the factor of change calculation gives us a factor of change of 9, not 3. And you can put the 3 squared over 1 in there as part of your expression. That's fine. You can refer to, in the kinematics equation, VF squared equals V naught squared plus 2A delta X, we solve with a final speed of 0 to get that the displacement is given by this expression. Then when I do factor of change, that's fine. Notice that I use subjects and verbs and that the equations were incidental to the subjects and verbs. That's what is meant by an explain in words, a justification in words, or a paragraph. And Declan asks, in the qualitative-quantitative translation part 3, what does it mean to describe the distance in terms of D1? That just means give me a mathematical expression that has a D1 in it. Imagine that D1 is, well, I think you misphrased what it said. It said solve for the distance D1 in terms of given variables and fundamental constants. That means you want D1 equals something where everything else is either given in the problem or is a fundamental constant like G. If the problem asks to solve in terms of D1, then that means D1 can be one of your variables in your final expression. Happy Enderman says, my physics teacher always says math doesn't matter. Is that always true? It is not. It is absolutely not always true. There is no way to game the AP exam. People will come up with all kinds of rules of thumb, but they don't always work. The only way to understand physics and to get AP exam questions right is to understand the underlying physics, is to know how to start with a fundamental principle of physics, like something on the equation sheet, to work through based on what is given in the problem, and then to use a skill that we understand, like graphing, like factor of change, like, if nothing else, plugging in numbers to see what happens, and then reasoning to an answer. That's the only way to solve physics problems. There is no way to game the test by saying, oh yeah, it's always friction, or mass doesn't matter. Those rules of thumb do not work. And how do we know they don't work? Because the people writing the test are physics teachers, and we know when those kinds of things are out there. Look, if you're ever asked on an experimental question in some other year, okay, when we do the experiment again, we get a different result. So why could that be? The answer is almost never friction. Why not? Because we know that every student's first grasp is, oh yeah, it's friction. And so we find things that's not the obvious answer. One more question, please. One more question. And let's see it here. Oh, can you show us the Edna fan art up close? Yeah, I can do that because it is absolutely beautiful. This is Edna and her friend Bertha, who is an elephant, and Anthony, who is not Edna's friend because he is a mean hippopotamus, and they are playing baseball when we all come back to school and we're all in happier times. Thanks, Aldiscary, for that. All right, folks. It is time now, and I think you did see that, right? There it is. There's the fan art. It is time, folks. I will be on Twitter for another hour or so. If you guys have further questions, let's talk about one more problem that we can give you. This problem here is going to be solved by Josh tomorrow. Josh Beck from North Carolina. You remember him? He was on last Wednesday. He was going to be on Tuesday, Thursday, and Friday of this week. And tomorrow, he is going to be discussing projectiles. What happens not when we have something moving in one direction, but when we have something moving in multiple directions at the same time. And although these are not projectiles on the screen here, this is a good starting point toward understanding the kinematics of constant speed and constant acceleration. It was originally intended as a qualitative-quantitative translation, but we're going to start with just drawing the graph and then doing sort of quasi poor person's qualitative-quantitative translation with explicit reference to physics principles and equations. Explain in a few sentences why you drew the graph the way you did. Justify the features of that graph. Josh will start tomorrow by answering this question. I will be back on Wednesday, and I will be talking about two-body problems. That is, when we have two objects that are connected over a string. And if we're lucky, Edna's friend Bertha, who is an elephant, might join us for that class. Until then, it's at Jacobs Physics, and we'll be back with you every weekday at noon Eastern Time, 9 Pacific time. Say goodnight, Edna.